It's nice seeing you. It's a great pleasure to be here. My name is Wojtek, and for the past year I've been working at a data science agency called EPR Labs, where apart from modeling heavy industry data, we have some pretty amazing internal projects. Let me introduce to you performance inference and node orchestration dataset, piano in short. A benchmark for inferring piano performances and modeling harmonical and dynamical structures in musical data in the MIDI format. I will show you how we use this dataset to create a controlled music generation task, and I will walk you through the full process of pre-training and fine-tuning GPT models on musical data, which is our method of solving the problems presented in this dataset. But first, I've got a question for you. Who among you can play the piano? Okay, amazing, amazing, very good, very nice to have you here. If you play piano or compose music, you are probably wondering, I like making music, why on earth would I want a computer to do that instead? Apart from the pure joy of training generative models, we do it simply because we are human, and humans have been trying to merge our understanding of mathematics and music for centuries, all beginning with Pythagoreans through Mozart up to Cage or Killer. But people before us unfortunately did not have gigabytes of GPU VRAM to train a model on. Moreover, you might have seen this notorious video of a gymnast generated with a model. And don't you wonder what a musical equivalent would sound like? You might have also seen this kind of artwork. It was training on X for about 3 days. A model generates images based on a mask provided by the user and some textual prompt like generate me a picture of a medieval village. How amazing would it be to do similar things with music? What we are doing is taking another shot at exploring the mathematical nature of music. So let me introduce to you our Piano GPT project, starting from the very beginning. This is a piano. A piano is operated using usually 3 pedals and 88 keys on a keyboard. Let's simplify it a little. Let's pretend that the piano only has a keyboard. And actually, during our experiments, we approximate the use of the sustain pedal, but still treat the representation as if it came directly from the piano keyboard. Think of it as a first-order approximation, and we can add precise pedal information later once the music generation system works with just the keyboard data. We are left with 80 pressing different keys with varying velocities causes the piano to create sounds of different pitch and varying loudness. Now the data describing the interaction of a pianist with a piano keyboard is a sequence of key presses and releases together with velocity information. And it's spread in time. And even slight differences in timing and velocity have a huge impact on how we perceive a musical performance. Some research suggests that humans are able to tell even 10 milliseconds differences when it comes to music. So when representing this data, we need at least 10 millisecond sampling rate. It is these emotional and technical nuances of tiny adjustments done by the performers when interpreting a piece written on a score sheet that make a composition, a performance truly beautiful and captivating. A piano roll that you can see here is a visual representation of such interaction. The rectangles start when the keys are pressed and they end where the keys are released. And a file format perfect for storing performance information as a sequence of events are MIDI files. MIDI stands for Musical Instrument Digital Interface. This is a format interpretable by electronic instruments. They store performance information as a sequence of events. So each time a pianist presses a key, a note on event is processed and so on. Pianos, thanks to their well-defined keyboard interface, where different keys correspond to different pitch values of the notes, can be very accurately represented using this format. And the performances and the emotional nuances they contain are very accurately represented. And here's how recording of a MIDI file looks like. You take your MIDI keyboard, mine is a miniature traveler's version, you plug it into your computer and start software for recording MIDI. Hold on. Okay. Then you hit record. You press the keys and rectangles appear on a piano roll, as simple as that. Then you can download it or you can play it back and you can represent a MIDI piece, a MIDI file, as a data frame of notes. A data frame where each row corresponds to one note played and each note is described with 4 values. Pitch, or a key number, which was used to play a note, velocity, which tells us how loud was the note played, start and end, which are floating point numbers. The code you can see at the top is how to load a dataset from Hugging Face, from one of the ones that we are storing on Hugging Face, and how to parse it to a form of a data frame. If you don't know Hugging Face, it is a platform for storing and managing your data and machine learning models, and it is free and super easy to use, as you can see. And this is how to visualize a MIDI file using Fortepian library, which is our library for managing MIDI files, and Streamlit Piano Roll, which is our Streamlit component for producing these beautiful visualizations that you can also play and listen to. Initially, we wanted to extend such piano rolls. We wanted to generate continuances of MIDI files, of some fragments of music. So, for example, here's how a 300 million parameter GPT model behaves when tasked to generate a continuance of fragment, like the one I've just recorded. All the notes in blue are prompt notes, so this is something that I played, and all the notes that are yellow are completely new, composed and performed by a model. So it's like, you know, large language models nowadays have billions of parameters, so this is really good, actually. Do you use large language models like ChatGPT or Cloud or Gemini? I see you nodding your heads, all right. If you use them, then you certainly know how they work, right? Either way, let me remind you quickly how GPT models train. They are trained on next token prediction task. By analyzing all the tokens before the current position, they predict which token should be inserted next. By analyzing all the blue tokens, they predict which the yellow token should be. During the first phase of training, called pre-training, they are trained on gigantic blobs of text, let's say whole Wikipedia, which is still just a fraction of what LLMs nowadays train on. Then, if we wanted to see if the model lands on geography, we should prompt it with the capital of France is, and hope it will output a valid answer, which is Paris. And this is how we prompt a pre-trained model. We wanted to generate a continuance of sentences. But this is not how we are used to interact with LLMs. We wanted to ask it questions or instruct them to do certain things. What is the capital of France? And this is how a pre-trained model might behave. Instead of generating an answer, it will output some continuation of some weird statement. And we cannot even be mad at it. This is exactly what it was trying to do, to generate next words, to continue statements. So, in order for us to gain more control over what the model produces when we ask questions, we fine-tune it in the second phase of training on question-answer pairs. This way, the model, after encountering a question, will output a valid answer once we train it to do so. This is similar to what we are trying to do with music, because generating continuances of notes does not give us much control over the music that we produce. We wanted to provide it with some musical input and make it generate a musical output based on the input that we give it, and to gain some control over what we generate, for example, by using control tokens in the middle. Don't worry about those tokens right now. What is important is that they are equivalent to fragments of music. I will show you that later. Now there is a difference between how the original transformer model works, original encoder-decoder architecture from Attention is All You Need paper, and how decoder-only architecture from OpenAI works and trains. Without delving into analysis of architecture, here is what is different during training. This is how original transformer is trained. It is trained, original transformer from Attention is All You Need was trained on translation tasks, and it was provided with two sequences, source and target. And by analyzing all the tokens from the source input and all the target tokens up to the current position, it predicted which would be the next target token. This is translation task, so this is a sequence-to-sequence task. By analyzing all the blue tokens, it predicted the yellow token. If we wanted to use an OpenAI decoder-only architecture for sequence-to-sequence task, we should include both source and target sequences in the input sequence to the model, like this. And then we just treat it as a normal next token prediction task, where we have one input and the model analyzes all the tokens up to the current position to generate an answer. We can also use a control token, especially if we want our model to do multiple languages, translation to multiple languages. And it also marks the beginning of a model's response. And this is even more similar to what we would want to do with music tokens. We want to use some control token that will tell the model which task it should be doing. Masked language modeling is a training strategy used to train models like BET, if you've heard about it. It involves masking parts of the input sequence and train the model to discover the deleted parts. It trains the model to understand logical and grammatical structures in text by analyzing, and it is treated like a sequence-to-sequence task. By analyzing all the blue tokens, it predicts which token should be inserted and which token was deleted from the input sequence. And that was exactly what was the NLP inspiration for defining masked language context-aware masking tasks for music. In this example, so the idea is to split the data frames of notes into two different data frames. In this example, we first calculate a median pitch, so a median key number, which was used to play the musical fragment. Then we treat all the notes that were played below this median as a prompt to the model, while we treat all the notes that were played above this median as target output. It sounds like this. So this would be the prompt to the model. And this is what we would want the model to generate. Music is inherently dynamic, so complex relationships exist between various elements in music such as pitch, rhythm, and dynamics. And by defining the tasks that represent these relationships, we train the models to understand them better. And just like in masked language modeling, we predict the deleted parts, here we predict the deleted parts of a musical sequence. And just as masked language models train to understand logical and grammatical structures in text, our models train to understand harmonical and dynamical structures in music. There are pitch-based tasks that operate on pitch values, which you can see on up the top row. We can split the notes based on medians or quartiles. There is velocity tasks that operate on how loud were the notes played, which represent dynamical relationships or isolate melody lines, which are often played louder than accompaniment. And there is, of course, a lot more different methods of describing and defining these tasks. And which means there is a lot of experiments to run and a lot of different methods of prompting the musical models to output us with something that we want. So we know what to do with the data, more or less, but how to gather the data? The majority of data you can find online is mechanical transcription of musical scores or music generated with MIDI software. It lacks the emotional nuances found in real human performances done on physical instruments. Here's what I mean. This is an example of a mechanical transcription of a piece written by Chopin. And here's a human interpretation. If you cannot hear the difference, then I don't know what to tell you. But I can show you. Here's a distribution of note durations, and as you can see, 70 out of the 80 notes used to play the mechanically transcribed fragment is the exact same duration. This is very boring, and human performances are much more interesting and varied. So mechanically transcribed music is actually quite fine for pre-training a model because it still contains a lot of information on the composition. But in order for us to generate music which is like real human performances, to even model music which is real human music, we need to fine-tune it on data packed with emotional nuances found in real human performances. The most notable dataset you can find is Maestro by TensorFlow Magenta team. It is 200 hours of classical piano repertoire from piano competitions. And it is 7 million notes. But 7 million notes translates to about 30 million musical tokens. The original transformer was trained on 200 million tokens. The GPT-1 was trained on 5 billion tokens, and GPT-4 is allegedly trained on 13 trillion tokens. So we need more. Fortunately, our company is actively trying to infiltrate the pianist community. We've prepared a social app for pianists, called pianoroll.io, which allows to track effort, to crowdsource MIDI data, and to track music generation experiments. For the crowdsourcing part, we are frequently doing competitions for pianists where they compete by ferociously practicing piano. And I also used this website to share my algorithmically generated music. And you can too. If you decide to share your algorithmically generated music, you might too get some feedback from real pianists that use the website, or you can roast my generations in the comment section as well. Thanks to this website and our collaboration with pianists, we are on the right track to gathering enough data for a successful model training with our internal datasets now consisting of 31 million notes, which is almost 200 million musical tokens, which is similar to what the original transformer from Attention History Unit worked with. And all the datasets combined, together with the mechanical transcript ones, are 4 billion musical tokens. Now I am going to show you and walk you through the process of pre-training and fine-tuning a GPT model, which is our method of solving the tasks and problems presented by the dataset. Velocity and pitch are integers, so they do not require tokenization, because we need to tokenize the data first in order to pass it through a GPT model. Timing is a float. We need to quantize it first. There are a lot of methods for tokenization, so you can visit our GitHub repositories to learn more and do more research, because there is already a lot of different methods. But here's what works for us. We define a set of time difference characters, which symbolizes different time differences. The minimal time unit is 10 milliseconds for the reasons I've mentioned before. We define a few of them, and then in order to represent a musical note, we use velocity token, which sets the velocity of the next event, note on, which marks which key was pressed, time tokens that fill up the time, and note off event, which means a note was released. This is how 8 notes look like, tokenized. What's important about this is that this sequence of notes is equivalent to this data frame of notes, or this musical fragment. If we want to take and tokenize longer fragment, this is what it would look like. So in order to tokenize 15 seconds of music, we need quite a few of those. This is more like an essay than a sentence. In order to pre-train a generative model, a GPT model, we tokenize our datasets and then randomly sample it and treat the training as if we would train it on text. So just a normal next token prediction task. To keep things interesting, we might also introduce a composer token. There is a lot of metadata which is stored together with the MIDI recordings from various datasets, so we can use this data to provide additional context to the training, which will hopefully train the model to use different composer styles. Then we treat it as a normal next token prediction task, which means that the model at each step will analyze all the tokens before the current position and come up with the most probable token for the next position. I'll take questions after the speech, sorry. A pre-trained model is capable of generating continuances of musical fragments. So, for example, all the blue notes are prompt, all the yellow notes are generated. We can also check out some different generation, for example, from Bach fragment. pre-trained foundation model, we can try and gain more control over what we generate by using fine-tuning. We wish for the model to showcase in its understanding of harmonical and dynamical relationships, or putting pressure on different aspects of a piano performance. And we wish to be able to control what it generates. For example, we wish to be able to prompt it with only the lower notes and make it generate all the higher notes. And that's what we use the piano dataset for, the soon-to-be ImageNet in the domain of MIDI. To remind you quickly, we split the notes into two groups. One will be used as a prompt, the other will be target. So, we first include both source and target sequences in the model input. First, we start off with prompt tokens, then we use some control tokens which will provide additional context and tell the model which task it should be doing, and then let the model generate all the tokens that it wishes to. This is similar to fine-tuning the model on like question answering tasks, which also gives us much more control over what we generate. But this is actually how this task will look like for more nodes in which we are interested in. So it's not really a sentence-to-sentence task. It's more of a essay-to-essay type of problem. We treat the task as normal next token prediction task, so it trains just like any other task on using GPT models. Then during inference, we start off with our prompt tokens. Then we include any control tokens that we wish that we defined and train it on, and then just let the model do its thing. And models fine-tuned that way are capable of inferring piano performances and producing only parts of fragments and producing subsequences of notes that we give to it. For example, here I used Chopin and above median control tokens, and it produced the notes above the median pitch, and this is what it sounds like. Do you want to listen to the original to compare it? Okay, I see you nodding your head. So that was the original. We can also swap the control token for extreme quartiles, which is a task for predicting all the tokens, all the notes above or below the extreme quartiles. And here's what it would sound like. Now we can also swap the composer token for something else. Maybe let's try Mozart. Now we can also use this to generate something from our own recordings of MIDI. For example, I went and recorded a peak of my piano performance. Right, you get the idea. And I told the model to do the extreme quartiles task in the style of Mozart. I also generated the same thing, but with Chopin control token. Okay. To sum up, what we did was we developed tools for parsing, visualizing, and analyzing MIDI data. We've developed some tokenization methods that we use to train GPT models. We've prepared data sets in an easy-to-parse format that can be represented in the form of data frames. We pre-trained GPT-2 models, we pre-trained and fine-tuned, and prepared framework for pre-training and fine-tuning and validating GPT-2 models on musical data. We defined downstream tasks, prepared performance inference and node orchestration dataset, which is a framework for task selection and made defining new tasks approachable, and we created a platform for pianists to track their efforts and to allow us to crowdsource musical data in a MIDI format. And now I invite you to play with them, to research our company at Hugging Face, to play with the data sets and our models. Our code is open source, but it's not really a pip install situation, so it will require some tinkering in order to get it to work. And if you like the tinkering part, I invite you and I strongly recommend you to contribute, because contributions are very welcome. And seeing you all at this conference, I've seen so much motivation and creativity. So scan the codes and let's see what we can do together. Actually, I will take questions. I think I'll take questions outside at the hall afterwards. We can have more time. I can show you more generations if you'd like. And yeah, have fun. Have a good day.